Hello and welcome. In this Max tutorial, we're going to build a polyphonic buffer slicer in Gen tilde. So before we start patching, let's quickly go over what we're trying to do here. The idea is to build a polyphonic buffer slicer in Gen tilde using manual voice management instead of MC tilde. So each playback voice stores and updates its own state inside of a buffer, which allows us to have multiple slices playing simultaneously. Besides being very useful just using this in Gen tilde, this approach is also valuable when MC tilde is not available. For example, if you're building something in Rainbow for the Bella or Raspberry Pi. The same design we're using here also closely resembles how polyphonic DSP systems are implemented in lower level languages like C++. So this makes this tutorial a very useful introduction in real-time audio engine architecture. This tutorial consists of 4 parts. The first one is just the setup, where we will create the window and also the buffers. In the second one, we will build a multi-channel phasor in Gen tilde. In the third one, we will do the voice allocation. And in the fourth one, we will then complete the playback. I am starting with an easy DAC and a live gain. Okay, let's start by creating our window function, because each of the slices from within the buffer will need a fade in and a fade out in order to avoid clicks. So I will first create the buffer, call this one window. Let's give this one a size of 1,000 samples. What we could do here is just say fill 1 and then apply Hamming. And then we can see that we have a fade in and a fade out. But for what I'm trying to do here, this fade in and fade out takes a bit too long. So I will create my own window. To do this, I will create a Gen codebox object. Within this object, we need to refer to the buffer window. And then I want to iterate over all the samples within the buffer, so over the 1,000 samples here, and then create a quicker fade in and a quicker fade out. In order to do so, we can use a for loop. We can say for I equals 0, I is smaller than the dimension of our window buffer, which is the 1,000 samples. And then we can increment this. And here in the for loop, for first I will create a ramp from 0 to 1. So let's call this one val for value. This is I divided by the dimension of the whole window. So okay, this one also needs an outlet or else it will complain. So let's just say out equals 0. And then if we bang this, nothing happened because we also have to put this into our buffer. So poke window value and then I. So what this does is first we specify the buffer, then we specify the value that we want to set, and then we specify the index. So going over all the indices, now we have this ramp going from 0 to 1. But this is also not the window I'm looking for. So what I want to do is I want to use a sine function. So I can multiply this one by pi, then say, maybe let's call this one fade. This is then the sine of our value. Let's bang this again. Oh, of course, this one needs to change. And then we can see that we have half of a sine wave. And now I want to apply an exponent to this. So this fading in and fading out is a bit steeper. So let's say fade equals power of fade, and then let's try 0.2. And now you can see that the fade in is very quick and the fade out is also very quick. Okay, then we can also use a load bang here in order to initialize this. And now we have our window here. Then let's create the next buffer, which I will call phases. And this buffer will consist of 8 samples. And each sample within this buffer represents one channel. So moving on to the second part, we can now implement our multi-channel phasor. In order to do this, we need a gen_codebox tilde object. Then, of course, on top here, we have to reference our buffer in order to access it. The idea now is that on every sample, I want to, so I have 8 different channels in here. Each channel represents one phasor, so one ramp going from 0 to 1 in a given time. And now I want to get the step, which is the amount we want to add on each sample. So if our sampling rate is 44.1 kilohertz, this code within this code box gets executed 44,100 times a second. And for each of these code execution loops, so to say, I want to know how much I need to increment my phasor in order to go from 0 to 1 in a given duration. And the duration will be determined by our sound file. So let's create another buffer, call this one sound. And here we can give it a file. So let's just take Zhongli. Then we can also put this in here, say buffer sound. Then in order to get the incremental steps per sample, we can say step equals just 1 divided by the dimension of our sound. But I think I will create a new variable, call this one duration, because we will need this a lot. So 1 divided by the duration. Then what we need to do now is essentially we're always taking the last value out of the buffer, then adding the step to it, and then putting it back into the buffer. And this way we have this memory of 8 different phases or of 8 different ramps for all of our different channels. So in order to do this, we can say phase equals peak. So we're looking into the buffer in our phases buffer. And for now, I will just say peak 0. So this means that we're only looking into the first sample, which is here like the first channel. Then we can say phase plus equals our step. So on every sample, we're advancing this by this step. Then I also want to clip it. So let's say phase between 0 and 1. So if we go past 1, this will just stay at 1. And if we go below 0, which shouldn't happen here, then it will just stay at 0. And then we can put it back into the buffer. So we can say poke. Then again, saying we're poking into the phase. No, wait, phases. buffer. And we're writing the phase value in this one at index 0, because now we just want the first one. And then we could output just the phase that we just created. Okay, this seems to be an older error. Then let's create a live scope object. So now this is just at 1 because the phase already went from 0 to 1. So what we can do to take a look at it is we could trigger this and say if input 1, so if this is 1, I want to reset the phase. So we can say if input is 1, we can set this to 0. So phases of 0, 0. And then if we're using a click, which is just a single sample spike, we can see that we have a ramp with the duration of this file. So this is essentially the main thing we need to do. So getting a value, advancing it, clipping it so it stays in the range between 0 and 1, and then putting it back in here. So in order to do this for all of our channels, we need a for loop. So we need to go over all of the channels and essentially doing the same thing. So in order to do this, we can say for channel equals 0, and channel is also smaller than the dimension of phases, which means 8. So we're going from the first channel up to the last channel. And then of course we also have to increment this. Then we can put the whole code we just wrote in here. But we also need to do some changes. So first of all, we're not only using the first sample or the first channel, but we're using the channel we're currently on. And the same thing we need to do here. So getting the current channel, putting it back in here. And looking into our buffer now, you know what? I will create a waveform object and then set this to our phases. And now we need a way to reset this, but I guess this is then already the start of the third part. So now we have this multi-channel thing implemented. And now I want to do the voice allocation. So essentially, I want to find the next free channel and then start the phasor within that channel. So in order to do this, so what I want to do, so how I want to achieve this is I want to send a number in here representing the part of the buffer we're playing. And then the channel will be allocated automatically. So in order to do this, let's maybe make a bit more space down here. So the idea is that we're, again, I'm sending in a single sample, but I'm using a trigger bang integer and I'm multiplying the sample by a number representing the part of the sound file I want to play. So if I'm sending in a 1, this gets multiplied by 1. If I'm sending in a 5, this gets multiplied by 5, and so on. So putting this in here. Now for our voice allocation again. So to trigger a new sound, we will just check our input here. So if input 1 is bigger than 0, we want to trigger a new sound. And in order to trigger a new sound, first I want to go over all of our channels to see which one is the next free channel. Free channel in this case means that, because imagine we're starting a sound, then the phase goes from 0 to 1 and then it stays at 1. So if the phase of a channel has the value 1, we know that it already played its sound, so it's free to use for us. So this is what I want to check here. So I can essentially copy this whole thing down here, going over all. And maybe let's also create a variable up here, call this one num channels. So this is a bit clearer, then we can put this here and also here. Oh, sorry, here. Okay, so going over all the channels. And then looking into the phase of this channel. So phase and then channel. And if this equals 1, we know that the sound has already played and that we can reuse this channel. So what do we need to do here? We can essentially do the thing I did earlier, mainly reset the phase. So let's say poke. Oh, sorry. No, that's not what I wanted. So poke. So into the phases buffer, a 0, and this is the index which represents our channel. So here, variable I is not defined. Oh, of course, I want it to be all fancy and call this channels or channel instead of I, and then I made the mistake of using I here, and the same thing needs to be done here. So phase is not defined, of course, because this one is phases. Okay. And also we don't have this phase variable anymore. So now we got rid of all our arrows. So, and now if I set a number here like 5, then nothing happens because I exactly did the opposite of what I told you to do. This one needs to be 1 because we want to check for a 1 here. And as you can see now, all of them are going at the same time because we're setting, all of them are 1, and then we're setting all of them. No, sorry. Yeah, all of them are 1, and then we're resetting all of them. But once we found 1, we need to break this loop, so only 1 gets set. So if we say 4, one of them goes, And if we put in a couple of numbers, you can see that we reset different phases. Okay. So what we also need to do is initialize all the channels, because when we close this max patch and then start it up again, all of these phases will be at 0. And then this whole system won't work. So in order to initialize all of them, we can use this neat trick. We can just say if elapsed equals 0. So the elapsed parameter essentially counts all of the elapsed samples from either when you reset the gen tilde or when you started the max patch. So if this one is 0, means only once this will be true, when we reset the max patch or when we started it. And then we can again go over all of our channels and set them to 1. So maybe use some commas. Initialize. This one is trigger new sound. And this one then, I guess, play all channels. So now that we got that out of the way, I think we can now move on to part 4, which is the polyphonic playback. So now everything should make sense soon, I hope. Yeah, in order to go to the last part and finish this thing, first we need another buffer, which is our window buffer. So we have our fade in and our fade out. And we also need a buffer, which let's call this one position, because now if we would use this as is, we would always start from the beginning. So each sound would be essentially the same because we're only going from 0 to 1, so playing the whole sound. But I want to play different parts of our buffer. So in order to do this, we need another buffer for each channel, or another value to read and write for each channel, which tells us, okay, what's the position for that channel. So let's also give this one 8 channels. Okay, let's call this positions. Maybe they belong together because they represent the channels, and they belong together because these are signals that we're reading. Then let's also create this buffer in here. Let's call it, I mean, we don't really have a choice. It's already set, it's called positions. Okay. And then yeah, the first thing we want to do is we want to decide how many steps maybe, but we already called this one step. So let's maybe call this phasor step to make it a bit clearer. And then we also have to change this down here. And now I want to create a parameter which can be accessed from the outside in order to say, okay, how many slices. I mean, we can just call it slices, I guess. So param num slices. And let's say we want 16 slices for now. And then when we trigger a new sound, we also have to decide on which slice to play from those 16 slices. So here to trigger a new sound, we will just access this buffer. So positions. And then we will set the position that we're sending in here. So if I'm sending in here a 4, I want to play the 4th position. So we can just say in 1. But okay, down here I want to start with 0. So if we have 16, you know what? This is also not very consistent. Let's call this one. I'm sorry for the confusion. So let's call this num positions. So we're slicing the buffer into 16 positions. And if I'm sending in a 4, I want to play the 4th position. If I'm sending in an 8, I want to play the 8th position. But for the playback, this will be 0 based. So it will go from 0 to 15. But here I'm checking, here it is, I'm checking if we're not sending in a 0. So we have to subtract 1 here in order to be again in the range of 0 to 15, or the maximum number minus 1. Okay, so every time we send in a number that is not 0, we will set the playing position accordingly. So we could also copy this and take a look inside. So positions. Okay, so now if we're sending in a 5, the first one would be 5. And if we're sending in multiple numbers, we can see that we're taking up multiple positions. And these positions, of course, the waveform only shows me numbers between -1 and 1. So this will be all clipped at 1, but it seems to be working. Okay, coming back to the final thing, I'd say. First, we need to change the number or the size of our step, because this represents the duration for the whole buffer. But now that we want to slice it into 16 equal parts, we have to multiply this by the number of positions, meaning that this phasor is now 16 times faster. So if I'm doing something like this, you can see that it's much faster. And then let's in here create our window, or use our window to create our fade. While I'm on it, this could also use some comments. Get and set phases. And then let's call this one fade in / out. So in order to create this, let's just call it fade. We're looking in our window function, or our window buffer. And now this is an important thing to distinguish. So here, when we're using the phases, or also when we're using the positions, the sample position represents the channel. So we're going over all of the channels for each sample. And here the sample position represents the actual sample in here. And in order to get that, we use window, then we use the phase that goes from 0 to 1. So phase. And then we need to say that the index also needs to be phase. And we need to interpolate in order to avoid clicks. So let's, I don't know, I guess I can get rid of this one. We can put this one down here, and then we can have a bit more space here. So what this essentially means is that we're not accessing the samples with their absolute index, but with a value between 0 and 1. And here we're accessing individual samples by their individual index. Okay, now we have the fade. Then we need to create the reading position. So now each of them goes from 0 to 1 in 1/16 of the duration of the whole thing, of the whole sound. But I don't want it from 0 to 1, but I want it from their actual position to, from the start of the position to the end of the position. So in order to do this, we can first, let's say, reading pause. First, let's get the offset. So the offset for this specific channel, we created it when triggering a new sound. And now we can we can get it back from this buffer. So let's, offsets. So looking into this buffer. And at this specific channel. And this will be, as I said, a number between 0 and 15. So in order to get an offset between 0 and 1, we need to divide this again by the, what did I call it? Num positions. So this is first of all the offset. And then to get the reading position, let's call this one reading pause. We need to divide, first we need to divide the phase for each channel by the number of steps, or again, the number of positions as we call it here. So again, instead of going from 0 to 1, this goes from 0 to 1/16, and then we can add in our offset, which means that we're going now from the offset we have to the next slice within our buffer. And now that we have the reading position, we can read this part of the sound file from the buffer. So read sound. So what do we call this? Maybe, no, we can't call it sound because the buffer is already called. Let's call this one grain. Again, we're peeking into this here, which is the same mechanic as peeking into the window. So we can essentially just copy this, because we again need phase because it's a value between 0 and 1, and we need interpolation, and we do not need the exact index. Then here, instead of window, we're looking in our sound. Instead of the phase here, we're looking into our reading position. And then finally, we can say output 1 equals our grain multiplied by our fade. And okay, we can't say it like that because this would mean that it gets overwritten. We have to say output 1 plus equals this, because we're doing this for every channel and then adding them up. But imagine that we're playing all channels at the same time and there is, I don't know, a transient on all of those channels. Then we will get values greater than 1 or smaller than -1. So let's divide this whole thing by the number of steps or by number of positions so it doesn't get too loud. Okay, that was a lot. I got an error here. Variable offsets is not defined. Because I called it positions. Okay. Then let's maybe, before we listen, let's use a live scope to take a look at this. So sending a 1 in here. Okay, seems like it's working. Okay. Okay, great. This seems to be working. So what we could do now, first of all, we could optimize this a bit because we're going over all the channels, even if they're not active. So maybe we could first check if the channel is active. So this is essentially the same check that we did here, but in reverse, because here we're checking if it's inactive or free, and here we're checking if it's active. So now we're checking if the current channel or the current phase for the current channel is not 1, then we want to do this whole thing. Okay. Okay, this is still working, good. And now we can, implement some kind of a playback system. An easy way would be to, I'm using a Metro now, but as we are doing everything sample accurate here, it's probably a better idea to do this in Gen and then just send out signals. But just as a quick demonstration, I'm doing a Metro here, say active 1, and let's say initial value is 500 milliseconds. And then we could use a counter going from 0 to 15, or no, from 1 to 16, and sending this in here. And maybe dividing it by all the positions is a bit extreme. Let's just divide it by 4. And the cool thing is that we can change the speed without changing the pitch of the whole thing, because each of those 16 steps will just play all the way through. So I think this is about the original speed, but if we go faster, you can see that the speed or that the pitch doesn't change. And here with the phases, we can see that we're still only using about 3 of the channels. So going even faster. Yeah. You could also use this system to create or to build a granular synth, because again, you can play multi-channel, all of the, or let's better call it polyphonic. You can play polyphonic sounds with this. All of the notes are ringing out. What we could also do, a last quick thing before I stop this tutorial, is we can also do like a random sequencer, let's say 17, so going from 1 to 16, and 0 essentially meaning not playing a sound. And now we have a fun breakbeat generator. Okay, but I think I will leave it at that for this video. As I said in the beginning, I think this is a very cool and useful technique. You can, first of all, build many cool things with it, and you maybe get a deeper understanding of how sample accurate polyphony can be achieved using Gen tilde. I hope you found this useful, and thank you for watching.